Welcome to the end of Cycle 7. Today, as before, we'll just be going through the propositions that are covered in Cycle 7 as well as some of the exercises in hopes that this will give you an opportunity to check your work and make sure that you're understanding everything as well as you should be. So to begin with Epicycle A, we've got propositions 7 and 8. And we have to remember in number 7, and I have a note about this in your book, that it's a counterfactual case, which means that it's presenting something which it knows to be false because it's a reductio proof. So to walk our way through 7, I will go ahead and draw out our figure for us, and then we'll go through the argument. So we begin, Euclid says, for if possible, given two straight lines, AC and CB, so there's going to be AC and CB, constructed on the straight line AB. And I'll label these in a second. So there's our first triangle. So now that we've drawn this, let's go back and read the enunciation quickly. He says, given two straight lines constructed on a straight line, so two straight lines constructed on a straight line, and meeting in a point, that's this point up here, there cannot be constructed on the same straight line and on the same side of it two other straight lines meeting in another point and equal to the former two respectively. So you can't have this line, a line of this length and a line of this length meeting in any point except for this point, right? That's the argument. So he says, for if possible, let this figure be constructed like so. And we have points A, B, and C. And now the if possible comes in where he says, and let's construct two other lines. So this is going to be AD and DB. And so what we're assuming then is that lines AC and AD are the same length. That's the assumption that we're making. So AC and AD are the same length. And of course, DB and BC are also the same length. Now, of course, I didn't draw them the same length because that's impossible, but that's the point of this, right? This is a reductio proof, so we don't have to worry about drawing something which is true because the whole point is, well, we have to draw it falsely. Therefore, our original claim was true. So let's go ahead and join that. I'm just skipping through the proof here. So he says, let's see, CD be joined. He says, then, since AC is equal to AD, and that's what I just said, this side is equal to this side, and therefore, by the way, this is what isn't maybe so clear, but because this side is equal to this side, even though we haven't drawn it that way, we have to pretend that these sides are equal for the reductio proof. And because these sides are equal, this whole thing, ACD, is therefore an isosceles triangle. So this triangle here, right, so our triangle right here, I'm tracing out in green, this is an isosceles triangle. And for the same reasons, by the way, the other triangle is also an isosceles triangle. So triangle CDB is also an isosceles triangle, right, which I'll sketch out in red here. So this triangle here is also an isosceles triangle. Why? Because side CB is equal to side DB. Right? Because we're assuming, of course, that the two sides are equal, and what we're trying to show is that point D cannot exist, right? That for a given side and another given side, these sides will meet only in a single point if they're placed upon a given base, right? They will only ever meet at point C. Point D is actually impossible. So to prove that, we've set this up, and we are able to say now, well, because these sides are supposed to be equal, this is an isosceles triangle because these sides are supposed to be equal here. This is also an isosceles triangle. And from this, we're going to conclude a couple strange things. So he says, then, since AC is equal to AD, and therefore an isosceles triangle, the angle ACD is also equal to the angle ADC. So this angle, ADC here is equal to the angle ACD, right? Why? Because these are both the angles at the base of an isosceles triangle subtending the equal sides. So those angles have to be equal. Now you have to resist the urge to see this as a three-dimensional figure. This is not a three-dimensional figure, this is a flat figure. And so obviously this angle is going to be much larger than this angle. That's pretty obvious just from the drawing, but we're going to prove that in just a moment. And then, of course, by the same reasoning, we have to say that the angle here, angle DCB or BCD, whatever you want to call it, is equal to the angle CDB or BDC. So these two angles are equal for the same reason, right? Because these are the angles at the base of an isosceles triangle subtending the equal sides. So Euclid says at this point, he says the angle ACD, so that's the angle ACD, this one here, that blue angle there, ACD is also equal to ADC, which is this blue angle there, the small blue angle there, the dark blue one. Therefore, the angle ADC, which is this angle here, ADC, is greater than the angle DCB, right? DCB, so this angle here, the light blue angle. So this dark blue angle here is greater than this light blue angle. Now you might say that's impossible. That's the point, right? But what we're showing is because the dark blue angles are equal and the light blue angles are equal, because the dark blue angles are equal and this dark blue angle is much larger than this light blue angle. Why? Because the light blue angle is only a part of the dark blue angle. Therefore, the other dark blue angle, which is equal to the dark blue angle, is also going to be greater than this light blue angle. And then what we conclude is therefore the angle CDB, right, this light blue angle there, is much greater than the angle DCB, this angle, the other light blue angle. But we know that these two angles are equal, right? So the reasoning goes like this. I'm actually going to redraw some of these angles so we can talk about them. So this is now going to be the red angle rather than the light blue because that's a little bit easier to distinguish. So the blue angle, right, the blue angle here at C is equal to the blue angle at D, but the blue angle at C is greater than the red angle there, and we know that this red angle at D is greater than the blue angle there at D. Why? Because the blue angle at D is only part of the red angle at D, but the red angles are supposed to be equal. So what we've proven then is that the small blue angle here is actually greater than the red angles, which obviously is false because this red angle is much larger than it. Or we could go the other way and prove that this red angle here is actually greater than the blue angle, right? Just depending on where you start. If the blue angle, according to this side, is greater than the red angles, then this blue angle is greater than this red angle, which is absurd. Or, to put it the other way, if this red angle is greater than this blue angle, and the angles of the same colors are the same size, then obviously this red angle must be greater than this blue angle, but that's also absurd. So either way we do it, we discover that the lesser is greater than the greater, or vice versa, and so this simply does not work. So what we have to conclude then is that the only solution here is that we made a mistake in saying that there was a point D that could exist where AD was equal to AC and DB was equal to CB, right? This figure cannot exist. The only place that lines AC and CB will meet, that any two lines equal to those two lines on this base will meet, is point C. Point D cannot exist. And that's the point of Proposition 7. So this brings us now to Proposition 8. And Euclid says here for the enunciation, if two triangles have two sides equal to two sides respectively and also have the base equal to the base, they will also have the angles equal, which are contained by the equal straight lines. So the figure that we have for this, we have a pair of triangles that are supposed to be equal. So there's one triangle. And I'll go ahead and copy over the other triangle really quickly as well. Okay, so here we have two identical triangles, and we're going to go ahead and label the points. So we have triangle ABC and triangle DE and F. So ABC and DEF. And so Euclid says, let these two triangles having the two sides AB and AC equal to the two sides DE and DF, and let them have the base equal to the base EF. So basically this side's equal to this side's equal to this side, and the base BC is equal to the base EF, right? So all the sides are equal to the respective sides. So what we're trying to prove, if the sides are equal, then the whole triangle is equal to the whole triangle, and that includes the angles, right? If all the sides are equal, the whole triangle, everything in the triangles is also equal. That's the claim. So he says, for if the triangle ABC be applied to the triangle DEF, and this is where you would have noticed that again he's using the same kind of language as he did in Proposition 4, this language of application, which we've already talked about. For if the triangle be applied to the triangle DEF, and if the point B be placed on the point E, and the straight line BC, so there's the base BC, on EF. The point C will also coincide with F because BC is equal to EF. Then BC coinciding with EF, AB, or BAAC, all right, so the other two sides are going to coincide as well with DE or ED and DF. For if the base, he says, BC coincides with the base EF and the sides do not coincide with each other, then they're going to fall at some other point, right? So he says, so if we place the base on the base here, right, if we apply the base to the base, everything's going to coincide. And this is where we get another small reductio proof, because he says if they don't, then we're going to get a point not at D, right? A won't coincide with D if this fails. Instead, A will fall somewhere else when we apply the triangles, and it'll fall something like this. And we're going to call that other point G. So if, when we place the base on the base, the whole triangle doesn't coincide to the whole triangle, you know, with the sides being equal and all that, then A is not going to fall on D, it's going to fall somewhere else like point G. Maybe that's where A will fall. But there's a problem, right? The problem here is that because the bases are equal and because AB is equal to DE and AC is equal to DF, by proposition 7, there's no other point at which A could fall except D. Because we know from proposition 7 that if you have two given sides on a given base, that there's no other point that the two lines could meet except at the one given point here, which in this case is A. So what Euclid is saying is if A does not coincide with D, it'll fall some other place at G, but that violates proposition 7. Therefore, there's no way that that would happen, and point A would always coincide with point D, and that would make the whole triangle equal to the whole triangle. And that's really the end of that proposition. So it's very much like proposition 4, but with the added argument based on proposition 7, which introduces a small reductio proof just to show that any other alternative actually is impossible. So proposition 8 is important because it's one of a set of 3 propositions dealing with the congruence of triangles. Proposition 4 is the first one, and it gives us what we usually call the side angle side theorem, or you might see this abbreviated SAS, side angle side, which says that if you have a side and an angle and a side equal to a side and an angle and a side, then the whole triangle is equal to the whole triangle. I mean, you know that because we've been over it. And then proposition 8 comes along and says, well, not only is that true, but there's one other relationship which is also true and works to establish congruence. And it's if you have a side equal to a side, and another side equal to another side, and a third side equal to a third side, that because the sides, the corresponding sides are all equal to each other, the whole triangle is equal to the whole triangle, and that includes all the angles in the triangle as well. So this we often abbreviate as the side-side theorem because of what it establishes. And there's one other proposition in book 1 that fits into this category. I'm not going to tell you which one it is because that's for you to find out, but there is one more that establishes a fundamental theorem of congruence between triangles. So keep your eyes peeled over the next few weeks and see if you can spot it. So this brings us now to proposition 9, which is the first of a set of 4 constructions, which are, of course, constructions 9, 10, 11, and 12. And you should have constructed all of these in your journal over this past week as well. So I'm going to go through them quickly just to make sure that the way you constructed them corresponds with the way I'm constructing them here so that you can check and make sure you've done it properly. So proposition 9 says to bisect a given rectilineal angle. So we begin here with a triangle, and I'm not going to walk through the entire proof, mostly just the construction, because I think that the proof is pretty straightforward. There's not a whole lot which is too difficult there, and so I think that you've probably been able to understand them pretty well on your own. So the main thing I'd like to do here is just walk you through the construction to make sure that the construction makes good sense to you. So we begin with this angle, right? So angle BAC is the angle that we begin with, and Euclid says thus it's required to bisect the angle. We have to cut the angle in half. That's the idea. And so we take point D at random, somewhere on AB. It really doesn't matter where we take it. I'll just take it there, because again, it doesn't really matter where we take it, just some point at random, so that'll be our point D. And we have to cut off from AC some point equal to D. Now, how do we do this? Well, we have to use, of course, proposition 3. Now, fortunately, this is going to be a very easy thing to do because all we have to do, like we've done before, is draw a very simple circle, and this circle itself will cut a C at exactly the same point as D. So that's a very simple application of proposition 3. I also went ahead and made this circle a dashed line because I think that it's nice to keep in mind that this is an intermediate step that does not actually appear in your diagram. So next what we have is we're going to join points D and E, and on D and E we're going to construct an equilateral triangle. So this is going to require us to draw a few more circles, but since this is just proposition 1, it's nothing new. We've done this before. And now I'm going to join these points here, and you find that in doing this, we now have point A and point F, which when we join them, we find have bisected the original angle. So this line AF bisects angle ABC. The angle has been cut completely in half, and so the angle on this side is now equal to the angle on the other side. So the green angle here is now exactly equal to the red angle on the other side. These angles are exactly equal to each other because we've bisected that angle. So that is proposition 9. It's a lot of fun, I think, to construct and not terribly complicated. Let's go next to proposition 10. So proposition 9 rather was to bisect an angle. Proposition 10 is now to bisect a line. So we're going to begin with our straight line AB. This is our given line, and we're going to cut it in half. So to do this, we have to construct an equilateral triangle on AB. Now this is pretty straightforward because it just requires 2 large circles because it's simply proposition 1. So we've drawn out our circles, and you should have done this, of course, with your compass, and you probably didn't have too much trouble with it because it is, of course, a proposition that you've done before. It's a construction you've done before. So now we have our equilateral triangle. I'm going to label point C. Now we have to find point D down here. And the way that we do this is by, again, using proposition 9. So there are 2 ways to do this. The first way is to actually go back to proposition 9 and reconstruct it, which is the way I'm going to do here first. So I'm going to choose some point on here. I'll actually draw my circle at the same time. So I'm just going to choose this point there at random, have another point corresponding there, and now I can draw my equilateral triangle on top, like so. Well, there's my line first. Now I need my other circles for the equilateral triangle. So there's one, there's the other one, and now I can join these points. And I hope you can see how this now is proposition 9, and then all we have to do is draw a line through this point, and this gives us, of course, point D right there. Isn't this a cool diagram? I think that these constructions are just really, really neat looking. Very cool stuff, especially if you do them in many colors. It's it can be really neat. So there we have it. So we found point D by constructing an equilateral triangle on our base, and then cutting the angle at the top of the equilateral triangle in half, and that has given us our bisecting line. Now there's another way to do this which is a little bit simpler, and maybe you've spotted already what it is, but I'll go ahead and show you. If we start over here, you'll find that there's a simpler form, a simpler way to do this, and this is that simpler way. So we begin with the same straight line, and we draw our circles here for the equilateral triangle. And to bisect, all we really have to do is join these 2 points. Now, why does this work? Well, it works because if I draw this in, you can see here's the equilateral triangle, right? But here we have a second equilateral triangle which serves as the same one that we built in proposition 9. So by simply joining these 2 points, we actually have proposition 1 already built into it, which is that equilateral triangle there, and then the equilateral triangle from proposition 9 appears as well right there naturally. So both propositions are still involved. This is just a simpler way to draw it. We have two circles, join the intersections of the circles, and so we still have proposition 1, proposition 9, but they appear automatically in the diagram, and it's not something we have to go to extra lengths to construct. So that's just a shortcut for bisecting a given line. Well, this brings us then to proposition 11, which is to draw a straight line at right angles to a given straight line from a given point on that straight line. So we're going to begin with a straight line, like so. And somewhere on line AB, we're going to have point C, which I'll just place there. So there's point C. Now what we need to do is, of course, draw a line at right angles to AB through point C, or perhaps I should say from point C. So how do we go about doing this? Well, the first thing we need to do is we need to choose two other points on either side of C, and they have to be in an equal length. And the way to do this is to just draw a circle, right? So this is going to be an application, a very straightforward application of proposition 3, where we're using proposition 3, which means just drawing a circle to cut off a given length. And so, of course, because C is the center of the circle, this point is going to be equidistant from C as this point is, right? These are going to be equidistant points from C. They're the same distance. So there's that. And because this is an intermediate step, I'm going to make the circle a dashed circle. So there's our dashed circle, and I'm going to label these points D and E. Now, the next thing we need to do, of course, is draw two more circles, because we need to construct an equilateral triangle. So the way that we're going to do this is by drawing two much larger circles here. There's one circle in red, here's going to be another circle in red there. So two red circles, maybe you can see that on your screen. And of course, that's going to be our point that completes the equilateral triangle. So we can join these points then, like so, and we have our equilateral triangle, and that makes this point F. So we have D, F, and E, and then of course we've got C down here. Now all we have to do is join F and C, and we are done. And then the proof, of course, follows, but I'm not going to walk through it. I think you can follow that probably pretty well on your own. So this is a much simpler diagram, actually, simply because it required fewer circles, because we didn't need to actually draw proposition 9 up here, because we're not bisecting the angle. We already have our point, and we already made two other points equidistant from that point by drawing our gray circle there, right? And then from that, we were able to construct this triangle and then drop the bisecting. And so this line really does bisect the angle, but what it's doing here is not so much bisecting, although that's true, as it is constructing a perpendicular line, right? We know that it's perpendicular because in the proof we're shown that this angle is equal to the angle on the other side, and that, of course, goes back to what the definition of a perpendicular line is, which if you don't remember, you'll want to go back and look in the definitions, but that's that. So why don't we go now to proposition 12, and I hope that so far you've realized that you've done the propositions correctly. I hope that that's true. If you haven't done them correctly, you'll want to go back and redo them the way that I've done them, just to make sure that it's all making very good sense, because if it isn't making great sense, you'll want to make sure that it does. These are really important constructions to be able to do, because we will be using them throughout the year. And if you don't get them now, you'll be very confused later on. So make sure that you can do these easily. If they're not second nature yet, that's okay, but just make sure that you don't have any trouble constructing them. And the more that you do them, too, the more fun they'll become and the easier they'll become as well. All right, so we have points A, B here. That's going to be our given infinite straight line. You'll notice I drew it as an infinite straight line because it goes off the screen on either side. So this is just an infinite straight line that I've drawn sort of at random. Chose 2 points on it, A, B, just so that we can have a name for this line. And C is going to be the given point, which is not on the line. So this is much like 11, except that here, rather than having the point on the line, it's off the line, and we have to drop a line from C to AB so that it's perpendicular to it. And this is one of the reasons, too, why, by the way, I advised you at the beginning to get a journal that was free from any kind of lines, right? Because if you have a lined journal, a ruled journal, you'll be tempted to draw these lines perfectly horizontal. If you look at this one, this line's actually slightly slanted. And that's not a bad thing. It just means that we really have to make sure that we draw a true perpendicular line and not one that merely looks perpendicular, right? Or if you have a journal that has a grid in it, a gridded journal, the temptation will be to rely on the perpendicularity of the grid pattern, right? The grid pattern, the perpendicularity of that, rather than actually focusing on drawing the figure correctly. Anyway, on we go. So we have C, which is not on the line, and we have to draw from C to AB a perpendicular line. So how do we go about doing this? Well, the first thing we have to do is actually choose some other point, which I'll just choose, and it has to be on the other side of AB. And if it's not obvious why it has to be on the other side of AB, if it's on AB, then there's a chance that it could be right there, and that the circle won't actually pass through AB. And if that happens, then the diagram doesn't work. So it has to be on the other side of AB that we choose that point. And that's going to be point D. All right, so we have center C, distance CD. There is our circle. And we're going to label the other points here as well. We still have to drop our perpendicular line. So how do we go about doing this? Well, we join these points here. So we make a triangle like so. And then all we have to do is appeal to proposition 10 to bisect this base right here. So we're going to bisect the base GE using proposition 10. Now proposition 10, remember, uses proposition 9. So I'm going to walk you through all the steps just to make sure that it makes good sense. And I'm not going to take the shortcut that I showed you earlier. I'm going to do it the long way, just to make sure that you understand how this is to be done. So we're going to bisect it like so. So we're going to drop that first. I'll do this all in dashed lines so you can see what your diagram doesn't actually show you. So we've got that, and we're going to draw our equilateral triangle like so. So there's our other circle and the other circle. And we can even join. Now I can really join these, any of these points that I wanted, but I'm going to do it like this. Because when you're using a ruler, you can line them up however you want. If you want to choose that point to get the diagram a little bit cleaner, and just set your ruler so that these 2 points are in a line, and sort of draw down from there, that works too. But I'm just going to choose my point down there. All right, so now I've got this, and I can drop my line to there. I'm going to go over it again with a regular line. So we're going to just trace this line down to there, and we find that we hit right there like so. So having done that, we can now be sure that this really is a perpendicular line. Why? Because we have bisected the base according to proposition 10. And having bisected the base, now of course we can walk through the proof given by proposition 11 to prove that this really is a perpendicular line. And again, I'm not going to go through that because I think that it's pretty straightforward, and we'll let that be the end of proposition 12. So next we're going to talk about propositions 13, 14, and 15 rather quickly, and then we're going to save some time for construction C and problem D, because I bet those are the things you really want to spend more time on. So very quickly, proposition 13, the argument goes something like this, which I'll sketch out kind of roughly, and maybe it'll help as you follow along. So we have this right angle there because we've drawn EB at right angles. So the claim is that if we have line AB set up on DC, right? If we start with that AB on DC, that the angle on either side of AB, these two angles together are either going to be two right angles exactly, or the angle on the one side plus the angle on the other will be equal to two right angles. So either they will be two right angles or they'll be equal. Now if they are actually two right angles, then it will be a perpendicular line. And if they're not, then the angles will not be two right angles, but they should still be equal to two right angles. And so the way that Euclid proves this is he says, well, if this AB is not perpendicular, let's draw a line that is perpendicular. So here we have EB, our perpendicular line, and that means that the angle there is a right angle, obviously. And also that means that the angle on the other side is also a right angle, but I'm not going to draw it in. And we have, of course, the angle here, which is angle ABC. Now this angle I've drawn in green. I'm going to draw one more angle, and this angle is going to be the whole angle on this side, which I'm going to do in red. And maybe we can even identify one more angle in this brown, which maybe you can sort of see and distinguish. So these are the angles that we're interested in. Now, the argument goes something like this, right? If the angle, the blue angle here, is a right angle, then we know that the angle on the other side is also a right angle, which means that the little brown angle there plus the green angle is also going to be a right angle. But because the brown angle is a part of the red angle, right, and the blue is also part of the red angle is equal to the blue plus the brown angle, which means this blue angle here, which is the right angle, which is equal to the brown plus the green angle, because that's a right angle there, is equal, or I should say the red angle is equal to the blue angle plus the brown angle, right? So it's a right angle and a little bit more. And that leaves the green angle, which with the brown is a right angle, but without is less than a right angle. And so what we find then is that the red angle plus the green angle is equal to the blue plus the brown plus the green. So either way we look at it, we always end up with two right angles. And so that shows us then that angle DBA plus ABC is equal to two right angles. Red angle plus the green angle is equal to two right angles, because when we break it down with our perpendicular, we find that on one side we have a right angle, on the other side we have what's equal to a right angle, and this second right angle on the other side, which is angle EBC, is actually broken up into two smaller angles, the brown and the green, which are parts of those other two right angles which we could draw there, because of course this whole angle there is a right angle, and it's just been divided into two parts by AB. So that's how we go about proving proposition 13. So the diagram for proposition 14 is similar, but we're moving in a different direction, right? The enunciation for this one says, if with any straight line and a point on it, two straight lines not lying on the same side make the adjacent angles equal to two right angles, the two straight lines will be in a straight line with one another. So in 13, we assumed that we had straight lines, and we talked about the angles. Here we're talking about the angles, and we're using the angles to prove something about the lines. So we begin with line AB, which I can draw something like this. Then we have two straight lines, BC and BD, not lying on the same side, like so. And we can label them C and D. And so the claim is, if we have these two, remember these are two separate lines. It looks like one straight line, but these are two separate lines so far, and we're going to claim that these actually lie in a straight line with each other because of the angles, because he says that the adjacent angles ABC and ABD, so the angle on either side, so this angle on this side plus this angle on this side together make, or are together equal to two right angles. And then the question is, if those angles together equal two right angles, does that mean that CB is in a straight line with BD? And he, of course, he's going to answer this at the end of the proof and say, well, yes. And we prove this, of course, with a reductio proof by assuming that these do not lie in a straight line. So if we say, okay, so if these don't lie in a straight line, then there's going to be some other line which makes the line straight. So now what we have is this green line here, which is going to be point E there. That line is now the continuation of the straight line CB. So you have to imagine that CBE is now actually a straight line. That's the straight line. It looks bent to us, but that's actually the straight line. That's what we're assuming for the reductio proof. So if then CBE is a straight line, because CBD is not a straight line, so if this is our straight line, what do we have to conclude? Well, what we have to conclude is from proposition 13 that a straight line falling on a straight line, that the adjacent angles are either two right angles or equal to two right angles, right? Which means that the angle here on this side and the angle on this side have to be equal to two right angles. But that's impossible. Why? Because we already said that the angle here and the whole angle here were equal to two right angles. That's part of the given. So there's no way then that BE could be in a straight line with CB, because it violates the principle we've already established in proposition 13. Those black angles cannot be equal to two right angles, because the larger angles, that is the green angles, those are already equal to two right angles, and we know that the black angles together are actually smaller. So those have to be equal to less than two right angles. So CBE is not a straight line. And the only line which is straight is CBD. So if we have then a straight line falling on two other straight lines, and the angles on either side of this straight line AB together make two angles which together are equal to two right angles, then we have two lines which actually lie in a single straight line. So now we come to proposition 15, which is a lot of fun because the diagram is very simple to draw, but it's also pretty neat, I think. So there's our diagram, piece of cake. And of course we need a center point, and we'll label all of these. So the claim here is if two straight lines cut one another, they make the vertical angles equal to one another. So these two green angles on either side of E, of course, are the vertical angles because they lie opposite each other at this opposite from this point of intersection, right? And of course these are straight lines. So those are the vertical angles. But the claim that Euclid makes here is that the angle AEC, this angle here, AEC, is equal to the angle DEB. So he wants to prove that these two angles are equal. That's what he's after. So he says since the straight line AE stands on the straight line DC, then of course together the angles on either side, so this angle plus this angle, are going to be equal to two right angles. That should make sense. So those two angles are equal to two right angles, but then we can say that the same is true of the other side. So then we can say, okay, well, that's true, but look, DE stands on AB as well, which means that these two angles have to also be equal to two right angles. So that means that this angle plus this black angle is equal to the black angle plus this other angle, right? And so the black angle plus the green angle is equal to two right angles. The black angle plus the red angle is equal to two right angles. And so if we just subtract the black angle, then we are left with equals, right? Equals subtracted from equals are equal. So if we just get rid of the black angle, then the remaining angles have to be equal to each other. So the red angle has to be equal to the green angle, and that's the end of proposition 15. Now, there is a porism attached to this, and a porism is just, and you have this footnote in your book, by the way, but I'll just tell you what it says. The porism is essentially another consequence that arises out of the proof. So it's something which is essentially proved along the way, even though it wasn't the proof that we were really after. And the porism in this case is just that if two straight lines cut one another, right, that the angles at the point of intersection form the equivalent of four right angles. And this should be obvious. If you just take what we've got here, we know that because of proposition 13, the black angle plus the green angle is equal to two right angles. The red angle plus the black angle also equal to two right angles. You add two right angles to two right angles, you get four right angles total. So that should be straightforward. Let's go back now and take a look at construction C. So rather than telling you the way to solve construction C, because I don't want to give the answer away yet, because there is an exercise in the future which will again reference construction C. Instead, I'm going to show you how not to do it. I'm going to give you one common way that this is done incorrectly. So students will often start with AB, like so, and they'll say, okay, so AB is the given straight line, and we're going to make a right angle with this as the base, and we need to have the side be twice the length of AB. All right, here we go. So then we're going to draw a circle like so, and we're going to extend this out to some other point like so. Now the reason that we're doing this, of course, is because we're going to construct an equilateral triangle. So we join these points then, right? And we draw these circles, and we get something like this. And we can connect these, and ta-da! What do you know? We're done. This side is twice the length of this side, and all that is peachy keen, except it isn't. And maybe you've already spotted the mistake, but this is not the way to do it. So I'm just going to bold these sides 1 second there so we can look better at what's going on. Now the reason this doesn't work is, or I should say the reason that this doesn't work should have become clear in the proof, right? If you try to write a proof for this, you'll find that the proof goes something like this if you're thinking about it carefully. You'd say, okay, so AB is the given straight line. And then what we did was we extended AB to point D equal, so or we can say such that DB is equal to AB, which we did with the circle, of course, right? So we can say that it's really proposition 3, sort of, and the postulate that allows it to continue drawing a line in a straight line. So sort of a combination of those, but we'll just write proposition 3. So next, we would have to say that on base AD, now I haven't labeled D, of course D is this point that I keep referring to down there, but on base AD, let equilateral triangle ACD be constructed. And then we're going to say, and let CB be joined. All right, so now we've written out enough to have our triangle. So there we have our triangle. So to prove that the triangle actually meets the requirements, that is to say that CB is twice the length of AB, we would have to prove that in some way. And if we tried to prove it, we would quickly run into a problem. So let's try that just so that we can see how that works. So if we were to try to prove this, we would say something like, okay, in triangle ABC, side CB is twice the length of AB. Now it's not enough just to say it. We have to say why. How do we know this? So in these brackets, what do we put? What's our justification for this? If we say that it's because it's an equilateral triangle and the sides of an equilateral triangle are equal, well, that creates a problem because that's not the side of the equilateral triangle. AC is the side of the equilateral triangle, right? And so you would quickly discover this is not a solution to this problem because the side which is twice the length of AB is not CB, it's CA, but that's not one of the sides about the right angle. There's the right angle, right? So we needed to actually have BC be twice the length of AB, but this hasn't done that. The side which is twice the length of AB is AC because we've bisected this side of the equilateral triangle. The other side is side AC. So this does not work as a solution, and if you wrote this out, you should have discovered this in your attempt to prove that you've actually completed the construction, right? So a good proof not only establishes what you've done, but it can also serve as a way to keep you from making these kinds of mistakes. Because if your proof is a good proof and you're being thorough, you ought to catch these mistakes as you try to prove that what you've done actually works. Because if it doesn't work, you should discover that in attempting to prove it. Because you won't be able to prove it, because it's not true. So this is how not to do construction C. This is wrong, okay? So don't do construction C like this. This is not how you do that. There is another way to do it. And so I'm not going to tell you what that way is, but if you did it this way, you'll want to go back and revise and revisit your solution and make sure that your proof really does work. This brings us to problem D. So in problem D, we have this. It says, let A, B, C, D be a square, and let straight line AC be joined, and also let straight line BD be joined. So I'm going to call this a square. Obviously, this is not a perfect square, but it doesn't matter. It really does not matter because this is a proof. It's not a construction, right? It doesn't matter what whether the diagram is perfect. What we're interested in is the logic. And so then we're going to draw in the perpendiculars, and this should have been the diagram that you constructed for this particular problem. Now what you have to do is you have to prove that A, C, and BD, these diagonals, are perpendicular to each other. To put it another way, you have to prove that at least one of these angles is a right angle. That's what you have to prove. Now again, I'm not going to tell you how to solve this one yet because chances are you haven't figured it out yet, and I don't want to keep you from figuring it out. Instead, what we're going to do is I'm going to tell you how you can't prove it. Now, one of the things that I've seen students do in the past is they will very cleverly try to prove this by drawing something. And so I've had students take this point here and they say, okay, well, maybe we can prove that this is a right angle by drawing a perpendicular line on top of it. So let's try that. So we have here, so we've got that. So this is really just going to be proposition 11, I believe, right? So do something like this. Huge circles here. And we're going to draw to there, and this line should be the perpendicular line. Now already you should see the problem, right? Because I didn't draw my figure perfectly, there's no way of knowing whether or not this line is going to pass through point B. Now I didn't draw a perfect square, so maybe it does, maybe it doesn't. If my square were perfect, would this actually pass through point B? Well, maybe, but we have to prove it, and drawing does not prove it, right? Because even though it may look like it passes through point B, if you zoom in far enough, maybe it will no longer look that way. Or if we zoom out far enough, maybe it'll look like it actually did work. So here we have a case where I've zoomed out quite a lot. And you can see from this, because I've zoomed out so far, that it's difficult to determine whether or not this line that I've drawn there actually goes through point B, which is the one right there. Maybe you can see that. Now if we zoom in closer, then obviously it'll be easier to spot. And you can see now that we're zooming in that, yes, those points do not actually coincide. Now, the reason I show you this is because any square that you draw, because it's a physical square, is not going to be completely perfect. It might be really close to a real geometric ideal square, but it's never going to be a perfect square. So just because a line seems to coincide with a point based on the way that you've drawn it, that's no guarantee that that line actually goes through that point. Now this is kind of an exaggerated case. Most of the time it'll be a lot closer than this, but I hope that you get the idea, right? Just because it seems to coincide doesn't mean that it actually does, unless we have some kind of logic to back that up. But if all we do is draw a figure on top of our figure and say, look, the line that we drew seems to touch that other point, that's not a proof, right? There's no certainty that there really is a true coincidence there. And so that's all that I'm going to give you here for Cycle D. later on I will give you the solution for it, but not today, because I want you to keep working on it, keep thinking about it, and avoid this kind of proof which really isn't a proof. Make sure that your proof really is based in the propositions that we've covered and in some solid logic. And so that's going to be it for today. And so until next time, work hard, and we'll see you after cycle 8.